Okay, so welcome everyone. It's good to be with you. It was good to be able to hold the lab session yesterday where we jointly built up a little model exhibiting heterogeneity. We're going to continue with that emphasis in lab sessions next week with adding some further model building to capture simple dynamics using a metaphor for characterizing state and transitions and evolution of that state called a state chart. And in today's discussion, we're going to be exploring some of the characterizations of state charts and some of their underlying mathematics. As time allows, we may further delve into issues involving scaling properties associated with capturing state and ways in which it impacts model transparency and model nimbleness. We have a lot to cover, and likely it will need to be spread between this session and the next session. So we'll dive in. Okay, to that end, I'm going to share my screen here, and we will get going. Many of these concepts you will see borne out in our coming lab session, and potentially some in models exhibited in class prior to that point. Okay. Class members will recall that agent-based models are defined by a set of characteristics. One of the most central of those characteristics is the fact that we have one or more populations composed of individuated agents, individuated individuals who are in some sense autonomous. Those individuals have characteristics and parameters that are often diverse, and that was the focus of Wednesday's discussion: heterogeneity, static heterogeneity. What we're going to be talking about today is elements of state and rules for evolving state. A later session coming next week will be discussing different metaphors for describing how we evolve state, different ways of characterizing it declaratively. Today, we're going to be focusing on one particular way with state charts, and we're going to be exploring its implications. That will likely continue next time before we get to a more general sort of reflection on different ways to specify state updates declaratively and imperatively. I will note that other characteristics of agent-based models, such as their means of interaction within spatial and topological contexts, their connection to others, aspects of the time horizon, and initial state will be the focus of future sessions. Okay, so let's talk about state in agent-based models. The very definition of a dynamical system is one that often refers to the central notion of system state, the fact that a dynamical system is a system that exhibits change in its state over time, or a system a little bit more specifically that updates its system state in a manner that depends on that system state. We can imagine systems that exhibit behavior over time that are not dynamical systems in that latter sense. For example, it just exhibits independent, identically distributed randomness at each point in time, right? Drawn from the same distribution. It's not updating based on its state. Or we can imagine a system which is completely deterministic in terms of its outcomes over time. Deterministic in the sense more than that. It exhibits the same output over time. It's constant, I should have said, invariant. That too is not fully a dynamical system, right? in the full sense that we often wish to use it. Where often the term dynamical system is used specifically to refer to systems whose evolution depends on their current state. How things change depend on what is the case right now. And whether you're characterizing stock and flow models, compartmental models, in other words, ODE models on the one hand, or agent-based models on the other, or for that matter, discrete event simulation models, they all share that general characteristic. That generally the update to the system is reflective, depends on the current state. We specify it in different ways. And as we'll see, even for ABMs, we'll specify it in different ways, how it depends on the current state. But this notion of dependency on the current state for how things change is a common feature of all dynamical system specification traditions. Now, with ABMs, the state is a more textured quantity. It's a more textured construct. It includes aspects of discrete state where you're evolving among different specific states, continuous state, where you might have a variable that encodes an approximation to a real number. Maybe it's your viral load and it's changing over time. Maybe it's my income level and it's evolving in some gradual way. Maybe it's a measure of the amount of fentanyl in my system. Maybe it's an amount of fatigue, an amount of stress that I feel right now. Continuous quantities that evolve continuously. This is a need for some ABMs. They're most commonly created in a tradition where we have discrete quantities, but very frequently we have continuous quantities that need examination. More than that, though, the elements of state can be relational, right? We can have aspects of connections between people. We could have my connections change over time. Perhaps they change over time based on my behavior. I start smoking and I start acquiring more connections that are fellow smokers. I quit smoking and I start spending more time with non-smokers or never smokers, former or never smokers, and my connections change. These relational connections which relate one person to another. Elements of state can also be positional. They're located at a certain point, and that point evolves in time. This is the province of mobility, and it will form the focus of future lectures. Mobile agents exhibit the introduction of mobile agents into a system compared to merely static agents has wide-ranging impacts on those agents, but often on dynamics across the system. For example, accelerating spread of infection or spread of information or spread of rumors, as people can carry these things from one place to another beyond any pre-existing ability for spread among situated stationary agents from one place to another. When we have mobility, we have different avenues, different pathways by which contagion, be it information, rumors, conspiracy theories, innovation, knowledge, attitudes, beliefs, or pathogen, can spread. So state in ABMs is a more textured construct than what we see in ODE models, for example, where we have continuous quantities associated with each stock, with each compartment. And it makes sense that our ways of specifying it are more textured, more varied. So the characterization of rules do differ a lot. And there's two primary traditions. One, declarative characterization. You specify what you want to be the case, what the relationships are, what the states are, what the means of transitioning between states are, what the rules are that govern those transitions. And the system takes care of interpreting those and making them and making them obtain, making them apply, realizing them, or imperative translations where code is specified to specify the rules. Or you don't specify it mathematically, but in terms of only implicitly in terms of code. The mathematics are implicit in the code. And there's different variants of those that we'll be looking at in future lectures. We'll look at different declarative characterization. But today we're going to be dwelling on one of those. And this will no doubt continue on Monday because it's a particularly versatile, increasingly widespread, and transparent characterization. And that concerns the use of state charts. State charts are used in multiple platforms. AnyLogic is the one we're using in this class, but Repast also has some representation of state charts. And they form an important construct, regardless of whether they're explicitly represented, reified as an object within these platforms, treated as something you can talk about, point to, refer to, create, reference explicitly in a model, or whether it's merely implicit in the code. So what is a state chart? Well, a state chart is a means of representing discrete agent, state, and behavior among of transitions among those states. A state chart specifies the following. It specifies with respect to a concern, a specific concern, like infection here, the set of possible states that you can be in with respect to that concern. Here, susceptible, exposed, infective, and recovered. The possible actions by which that state could change. So, for example, moving, if you are in the exposed state, this is a conditional construct, right? If you're in the exposed state, you can go to infected via this transition. You notice that the source of a transition characterizes a precondition for transitioning, right? You're not going to take this transition if you're susceptible. You're going to take this transition only if you're exposed. It's characterizing an action that can bring you from exposed to infected. And your ability to take it is contingent upon you being in that sort of state. You're exposed. Thirdly, so again, state chart characterizes states with respect to a concern, the actions that can change those states, and the rules governing those actions. And what you see here are indications with these icons of the types of rules that apply. Okay. Now, with respect to a concern, I should note that a state chart characterizes a mutually exclusive and collectively exhaustive set of states with respect to that concern. And what I mean by that is they're collectively exhaustive. This is the full set of states that you can be in with respect to the infection concern. And they're mutually exclusive. If you're one in one, you're not in another. Now, there's an asterisk here. And we'll introduce compound states, which give a hierarchical characterization in just a few minutes. So it follows with respect to these simple states, with respect to a given state chart with simple states, an agent is in exactly one state with respect to that state chart at a time. And over time, they move between those states. It further bears emphasis that a given transition here, when it fires, it's conceptually instantaneous. What I'm not So don't get that confused with me saying that you go immediately out this transition when you come into the state. I'm not saying that at all. I'm saying when it comes to the transition time to go from along this transition, this action of changing state, you don't spend time in that. It's not like you're in this pipe and you're stuck there for a while. No. When it comes time to transition, it's an instantaneous transition. Now, this transition may not fire for a long time. For all, in fact, it could even be that it never fires at all in the model, that it so happens that you never get in a situation where you're exposed, or that you stay in a state like recovered perpetually and you never become susceptible again. But the point is, when it fires, it transpires immediately. Now, I want to highlight to people, and this is important, I find that when newcomers come to state charts, there's some rookie mistakes that they make. One is to try to compress into a single state chart issues that are best factored into multiple state charts. And we're going to come to that point in a minute. It's one of the strengths of state charts, so we can factor them out into multiple state charts with an economy of specification. But another common mistake is to label as a state something that's conceptually a transition. So they might create a state for something like under recovery, and they show it as a state, but what they really mean is a transition. It's a transition between two states. And the way in which they're using it acknowledges that it's a very brief state. Often they make it ephemeral, like it occurs very, very quickly. But it's much more elegantly represented as a transition. So you want to be careful about what's a transition. Conceptually, these are things that when they happen instantaneously, versus a state, something that you're in for some persistent amount of time. And another example would be starting to smoke as a state. You could have early stage smoking as a state where you've been a smoker for less than a year, first year of smoking. That could be a state. But the actual act of starting to smoke is not itself not a state. It's a transition. It's actually okay. Now, I don't want to dwell on the specifics of state charts as a mechanism. We're going to come back to them. I will say there are many types of transitions that we can distinguish, many types of rules that can govern a given transition, a given action that changes people from a state. And these rules, these types of transitions, have quite a lot of flexibility compared to what we can characterize within compartmental modeling. And most notably, beyond memoryless transitions for which you have the same, if you're in a state, you have the same chance of leaving per unit time, no matter how long you've been in that state. That would be a memoryless transition. It doesn't matter how long you've been here, you have the same chance per unit time of leaving. If that's the case, that those are similar to what we can have in compartmental models. By contrast, if there's a variable rate, a rate like that, where this is changing based on how long you've been in that state, which you can realize, if there's a transition which says you won't leave this state for exactly some amount of time via this transition, those are both memory full transitions. In fact, that latter one, right? This one would say, for example, you undergo recovery unless you leave for some other reason, you undergo recovery in exactly, let's say, 10 days. This is the timeout transition. There, it's not only not memoryless, it's about as memoryful as it can get. Your chance of leaving in a given time unit is entirely depending how long you've been in here. A memoryless transition, it doesn't matter how long you've been there, you have the same chance per fill in the blank for unit time per day as when you got in. By contrast to memory, a timeout transition, you will leave in exactly that amount of time. It depends entirely only on how long you've been there. Assuming that you're not leaving via any other transition. As we'll see, there's some other types of transitions, some reflecting asynchronous factors like interaction of other agents. In some cases, so this might be a interaction with the healthcare system that confers treatment to you. This might be natural recovery. This might be you've been conferred treatment and you therefore recover by virtue of that treatment. Also, agent arrival in a mobility context will also make use of these. I don't want to dwell on this very much. We'll be seeing them in tutorials in the labs. But they are important. I will note that there's also a conditional transition. Okay. I'm going to skip a little bit forward here because we're going to be coming back to that. I want to talk some about some further fundamental understanding of state charts. First, by introducing compound states and then going on to talk about the mathematics of state charts. So beyond having types of transitions, we have sync states or exit points within a model, right? Commonly, those are used to place the agent either into a frozen sort of perpetual state or simply remove them from the model. And in some modeling traditions with UML, these can be shared between multiple state charts. I think the latest version of AnyLogic, you cannot share these between state charts now, although you used to. That's my conclusion after experimenting with this one. Okay, but really what I wanted to introduce was the notion of a compound state. Compound state is it's a type of state that in general can contain other states. It's a little bit like a hierarchical state chart. Should have introduced entry points within state charts that within a given state chart points to the designated point of entry. It can also point to a branch, and branches are constructs that allow us to route when we exit via transition to different resulting states according to some logic. We'll be dwelling on those more at a later lecture. But when we have a compound state, we also need a state chart that will say when we come into that compound state, whither we go. Where do we start? Where do we start? So what you see here are examples of compound states in each of these separate state charts. And I want to highlight a few features. Feature one, a compound state can contain other states. So someone who's in the correction system can be in it in a detention context, perhaps in the police lockup, in the Huskow for a short time, or they can be in it for a longer term period. Okay. Someone who is a former user of illicit substances could be under treatment or not under treatment. So we can have compound states with substates that are among among those who are in this state, it further distinguishes states and transitions between said states under that broad condition laid out by the hierarchical state. You notice sometimes these transitions can be rather articulated. Okay, so that's one matter. A second matter is that you have this entry point, a designated entry point that specifies where you start within that compound state. A third feature is that you can have entries to this state chart and to this compound state chart that go to it as a whole, and it will then route you to the appropriate state within it. So, for example, if I go into the correction system, I will here in short term and then go to long term is what this is positive. Under certain conditions, I go to long term. Maybe I start in police detention and then I may be placed in it for the long term. But you can also have entry points into it from outside, say this one with respect to the healthcare system, that can place me into a certain state in that compound state. So I'm outside the healthcare system right now. I'm not in a residential or overnight capacity in any one place, but I could be placed in long-term care. And here we might distinguish a transition into this specific state. Thirdly, and very importantly, for expressiveness, a compound state can exhibit transitions out either from the state as a whole. An example would be this state, where you have transitions out, or from particular states, examples being visible here. Now, or over here. Now, those bear some discussion. A transition out of the state as a whole, such as you see here, is saying that that transition can occur from any substate. If you're in any substate, you're eligible to take this transition out under the conditions under which it applies. It applies to you in any of the substates. That's the meaning of showing it as leaving from the state as a whole. By contrast, if it's from a particular substate, like this one, it's saying, well, you're in that particular substate of this compound state, you're eligible to leave via these processes. So the fact that we can group several transitions out of the state as a whole gives us a certain economy. And I thought I had a nice picture. Okay, I don't know why I thought I'd moved it earlier, and I apologize. It looks like I didn't, and either that or it's hidden. Okay. There's a rather nice, here it is. Yes. Here, for example, we might have for characterization of the life cycle associated with white-tailed deer. I think that's white-tailed deer. Their age group, whether they're a fawn or an older deer. And any of these states, at any of their age courses, they're subject to predation and they're subject to death from natural causes. And so rather than having a transition out from each and every one of these states, which would be pretty brutal, but more to the point, it would be an obscuring amount of detail. It would be easy to not notice mistakes or not notice oversights with it, to be inconsistent. It's just brutal repetition of the same pattern. It's easier to characterize it in terms of a transition from that overall state. And as you might sense from this diagram, you can secure a great deal of economy by structuring state charts suitably and by having transitions from them from the group state charts rather than from individual states within the state chart where possible. They also provide a certain modularity in understanding the code, a separation of concerns. I'd highlight here, for example, we have aspects of served behavior, deer behavior. And here we have, for example, a fawn stage. There's also a process that applies through later stages of eating, wandering for food to eat, and going to water. So mobility based on that. And then there's seasonal factors such as social movement in the summer or movement in the season known as rut, whereby there's mating related behavior that is often rather pronounced and far reaching. Okay, I was trying to move that so more was visible, but I failed. Okay. So what we have here with compound states is the ability to characterize with an economy of mechanism movement between different states. And this is giving me a bit of trouble. Okay. So state charts, we characterize different components, entry points, exit points, individual states, transitions between them of multiple sorts, compound states, branches I alluded to, which can be either at the initial point or at certain points in the process, which can route you to different places. And we talked about transitions with respect to both into and out of compound states. Mm-hmm. So we have a fair first glance parsing of state charts. State charts are frequently positioned side by side to achieve an economy of expressiveness with respect to different concerns and to allow for a separation of concerns. So we might have a state chart with respect to TB, to tobacco use, and to diabetes, for example. And each of them has their own sphere of focus. And the fact that we are characterizing them separately does not imply that they are independent, entirely independent of one another. For example, tobacco use can worsen the risks associated with tuberculosis, and there's some evidence that diabetes can, particularly late-stage diabetes as well. Tobacco use can interact with diabetes. But the fact that we factorize them into different state charts lets us, in each state chart, depict a certain set of dynamics and lets us depict the entirety of states and the transitions between them with less combinatorial blow-up. And it's to that point we're going to turn now. So I want to talk some about properties of state charts algebraic. State charts, you might not think of them as algebraic structures. You might not think of them as having mathematics associated with them, but they do. These are mathematical structures. They're structures that exhibit properties, that exhibit certain regularities in terms of their behavior, and that have certain equivalences between them, certain relations between them that identify one state chart as encoding the same information as another. they have a formal mathematics behind them. And I'd like to, without exhaustively treating it, I'd like to at least introduce it here in our remaining time. So a single state chart, say the state chart was susceptible and infected, can have a characterization with respect to its states alone, if we just focus on what states it has, or what state you can be in. You can be in either the state of susceptible or the state of infected or the state of recovered. And the way in which we write this mathematically is as what's called the coproduct among us. It's kind of like a set where you can either have this or have that or have that. So a given state here can be characterized as having this disjoint union or coproduct among the different states in terms of its possibilities, in terms of the value you can have. If you have parallel state charts, like these two here, and forgive me for drawing them out, on a board here. If we have SIR with respect to this state chart, and we have no heart disease and heart disease with respect to this state chart next to each other, we can think of the states for this first one as being characterized by either being an S or I or R, and this one here being in either the no heart disease state chart or the heart disease state chart. I put D bar according to the tradition, and you sometimes see in logic, certainly you see it in computer engineering and Boolean signals where we put a bar over to indicate not. So no heart disease, heart disease. These are the state possibilities for this state chart. These are the state possibilities for this one. And putting them in parallel is the states for that parallel combination are given by the product of these. The product of these sums. And products in this state chart algebra distribute, just like products. If we have products of sums of real numbers or natural numbers. So we can characterize these two state charts next to each other as encoding the same information as a single state chart characterized by their product here. Again, with this distribute. So how am I calculating this? Well, S, you know how to do this if these were pluses of numbers and times of numbers, right? You would have this S times not D. So those who are susceptible without heart disease is this state. Those who are in this state with respect to this one, I should have, and forgive me, better late than never. When you have two state charts next to each other, I want to emphasize, I think I alluded to that fact, but I really should have brought out that you're in one state with respect to each of them at a time. So I'm in one state with respect to tuberculosis, at any given time, one state with respect to tobacco use at any one time, one state with respect to diabetes at any one time, right? Same thing with here. I'm in one state with respect to the corrections system. I'm in one state with respect to the healthcare system. And I'm in one state with respect to the degree to which and conditions under which I use opioids. It's not like by being in the corrections system, I am not engaged with the healthcare system. Here, we can be in we're in one state with respect to each of these. Same thing here. When we have state charts in parallel, we are in one state with respect to each of them. Each characterizes a certain concern. So let's get back to our algebra of state charts or mathematics of state charts. What I'm saying is, if I have this state chart here, this state chart here, the states I can be in at any one time are one state with respect to this one and one state with respect to this one. And so I could be in, and this is what the algebra gives you, right? If I multiply this through, this plus this times this, if you just take the distributed property, we get S times not D, plus S times D, plus I times not D, plus I times D, plus R times not D, plus R times D. Those collectively enumerate the different states I could be in. I could be susceptible and not without heart disease. I could be susceptible with heart disease. I could be infected without heart disease. I could be infected with heart disease, and same thing with recovered. Now, I could draw out the state chart, which I'll call the normalized state chart, which combines both these two. The state chart characterizes the state with respect to each of these two, albeit in a somewhat more cumbersome and less and more verbose manner. We have each of these states, and let's think about where the transitions go between them, right? The transitions, there'll be a transition from one state to the other, if and only if, Jeff and Meti here should be thinking about products. There'll be a transition from those susceptible without heart disease to susceptible with heart disease, if and only if there's a transition at once from susceptible to susceptible, yeah, okay. You could stay in susceptible, so there's always an implicit transition there. And then from not diabetes to diabetes, there has to be a transition. So this transition would reflect staying in susceptible and going from not diabetes to diabetes. In general, we could think of a state as having a transition to itself. And what we're looking for in any judging, if there's a transition here, for example, is there one from susceptible, not diabetes to infected with diabetes? Well, we'd have to go here both these transitions. And so actually by rights, we should have driven one because there is one from this to this, and there's one from not diabetes to diabetes. So I actually should have drawn one here. By contrast, there's no from S to not D. So susceptible with no heart disease to recovered with heart disease. No, there's no transition because you can't go from susceptible to recovered. Although you could from not heart disease to disease, that you can't go from susceptible to recovered. So there's no transition down here. There is one, and there should be one shown, and I apologize here, between this one. I'll just draw that in to avoid confusing people. There we go. Okay. Okay, this may take a while with them. So we could systematically map out where we can go, right? There's one from recovered with this heart disease to recovered to susceptible with heart disease, because you can stay here and you can go like this. Recovered with heart disease and susceptible with heart disease as a transition. Now, this information within the state chart here to the right characterizes the same information as this state chart, these two state charts here. It characterizes the possibilities. It characterizes the transitions amongst those possibilities. But it does so in a somewhat more verbose way. You'll notice that collectively, these ones over on the left here have 5 states between them. 3 here, 2 here. On the right, we have 6 states, right? Those states come from the product of all possible states here. S, and each of these could be combined with each of these. You see them, in fact, right up here. This state chart on the left, this normalized state chart, does contain the same information as this one on the right, on the left. So the one on the right contains the same information, but in a way that is more, how shall I say? It's more verbose. It is less compressed. It's less parsimonious. We can factorize this state chart, just like we can factorize this expression into the product of these expressions and have a more abbreviated but equally correct characterization of the same system. What's on the left here is factorized. It's a more elegant way of describing this. It identifies the commonality here, the common rules behind the scenes. There's a common rule behind the scenes on the right here that we can't immediately see because there's just so much detail that, for example, any any state of not heart disease can go to a state of heart disease. That if you trace through here, that is in fact the case. We can find the indications of that. Here we go for recovered. Here we go for susceptible, right? Here we go for infected without heart disease to infected with heart disease. All of those have this ability to develop heart disease, but it's spread out. It's kind of distributed here within this in a way that doesn't bring it out. Here, it brings it out. It crisply specifies that. Similarly, implicit within this is the fact that whenever you're susceptible, you can develop infections. But here, it's characterized more directly. It's characterized in a more parsimonious, simple, clean way. So you could argue that just as this whole expression here can be reduced somewhat more elegantly to this one, with a separation of concerns also being achieved. This deals with infection, this deals with heart disease. So it is with the ability to characterize the state of an individual into multiple concerns. Now, I've shown it here with two concerns. Infection on the left, heart disease status on the right. I think you folks will likely know where I'm going at this point. If we had an effort to incorporate in diabetes status beyond that, or something with progression of retinopathy, or something with TB, right? Or tobacco use, tobacco use, never smoker, current smoker, former smoker. The combinatorics would get explosive here, and we'd be lost. The structure, the inherent structure here, would be lost in this detail. The hidden structure behind it, the latent structure, would be hidden behind here. It would only be peeking out. I shouldn't say it's a latent structure. It's a structure that should be evident, but it can be lost in the welter of details. Especially as we add more, just the detailed complexity of what's on the right can overwhelm, and you miss the commonalities. You miss the forest for the trees. What we capture here on the left is a more parsimonious way of factorizing it. And we get that separation of concern. We could discuss this with a communicable disease expert. We could discuss this with an expert in terms of heart disease. Okay. I will note, time is running short, but I will note that there's a further algebra of compound states. If we have, for example, an overall state and then a compound state. So this is not a compound state, but we have a transition into a compound state with a certain entry point. And then a transition out of that compound state. We can note, as we did before, that this compound state is characterized as sort of the matter of its states are characterized as the disjoint union or coproduct of B and C. It can be in either this or that. The whole state chart could be expressed as A plus BC, like you're either in A or you're in state BC, but that can be further unpacked into A plus B plus C, because that's what this is. There's a kind of equational reasoning that comes in. We could say the state chart shows someone in A or they're in BC, state BC, and that's true. But within BC, they can be in either B plus C. So this is equally true. Here, a transition out of this state as a whole. You remember I talked about that. You can have transitions out from particular substates or from the state as a whole, the compound state. If it's a transition out from the compound state as a whole, then it's coming out from B plus C to A. Now, this is not going to speak to some people here, but it will speak to some here in the room, for example. Some of you may know, if you have a choice between possibilities here, if you have a disjoint union or coproduct, B plus C, in order to specify a way of going from either B or C to A, it's the same as specifying a way from going from B to A and away from going from C to A. So it's the same as specifying a transition from B to A and from C to A. What that's saying is that you are able to go, if you have a transition from BC, you can go either from B to A or you can go from C to A. And the way we can write that actually is in this sort of notation. And I won't get into explaining the algebra of this, but it's basically talking about a means of going from B plus C to A. And you can actually factorize it. The algebra works that we're used to as, if we have A to the B plus C with, familiar algebra, that's the same as A to the B times A to the C, right? These are equivalent. And indeed, that's what this is. This map here, this way of going from B plus C, either B to A or C to A, is that information. If you need to specify how you can get from either B or C to A, it's the same as specifying the ways of getting from B to A and the ways of getting from C to A. And this is a way of getting here from this to this. So there's an algebra of compound states that I won't get into, also from going into it with respect to the entry point. Okay. So let's see what we're doing for time. Okay, I think what we will do here is I want to comment a bit, particularly for those who have seen ODE models before, models involving ordinary differential equations or compartmental models or stock and flow models, whatever you call them, these constructs, where we count the number at any one time or susceptible, infected, or recovered, and where there's flow between those. And let's compare it here to this state chart on the left. At a certain base level, at a certain first glance, these may seem equivalent. The structure looks directly comparable. You might be forgiven for thinking that the information of this one is the same basically as the information from this one. Same state transition, the same decomposition into possibilities, possible states. Where there's a transition here, there's a flow here. You could easily be fooled into thinking that these are just two different names for the same thing. It's understandable, but it's wrong. And we're going to be talking next time. We only have 3 minutes here, and I'm not going to be able to go into it any significant amount about really what the difference is between these. Even though there's a direct similarity in structure, they have very different implications. And particularly, I will highlight different implications for the organization of a model, but also different implications for what it means when two things are next to each other. Two state charts mean something next to each other, where an agent is in a specific state of the first and a specific state of the second. It's very different in what it depicts than if you have two stock and flow models or two compartmental models next to each other. Right? If you think about it, a given person is not in one thing here and in one thing here, just counting the number in each of these. And it's not keeping track of how many are in this state with respect, infected with respect to flu and susceptible with respect to COVID. It's not characterizing that at all in a way that it would. By contrast, it would in a pair of state charts next to each other. More than that, if we do want to capture that information in stock and flow models, we go down the way of the curse of dimensionality. Because we have to move beyond presenting these side by side, and we have to present their product of them. We have to present the systematic ways that you could be with respect to one and the other for each state. Technically, we can do it with a pullback, as Nathaniel knows, but the basic deal here is that you need to keep track of where how many people are in this state here and that state there, or how many people are in this state here and this state here. How many people are here with respect to this state here and this state here? How many people are in each combination of states? More than that, you have to specify the transitions in both directions. This direction characterizes the transitions along the COVID spectrum, along this one. This direction, this dimension, specifies the transitions along the flu characterization, where someone might stay susceptible for COVID, but develop successive points along their flu progression, along the natural history of flu. This progression, they're progressing in COVID, but staying the same with respect to their influenza status. So here, we are dealt with the curse of dimensionality. We have to deal with combinations of things in a way that's very different from what we deal with state charts put side by side. So I'm going to be commenting on that a little bit next time, and putting that into perspective and talking about the scaling that it implies. Because here too, just as Wednesday, we talked about the scaling, the adverse scaling of representing heterogeneity, static heterogeneity in stock and flow models. The fact that we need to keep combinations for each heterogeneity category, the fact that we can't characterize continuous progression, we can't characterize relational characteristics. We have to modify across the entire model to incorporate more heterogeneity. Here too, we will have deep constraints, but much of them have to do with just the sheer overload, the sheer obscurant nature of combining these things. The fact that this obscures the underlying model structure. It obscures the logic of each progression, and it requires any change to that progression requires changes across all this structure, which is painful to say the least. Okay, that's all we have time for today. Let's plan on reconvening on Monday finishing up this topic and talking a little bit about other traditions for specifying beyond state charts, declaratively characterizing the evolution of individuals within models. This coming Thursday, in lab session, I would encourage people to come to lab. We're going to be using state charts and exploring additional mechanisms for capturing state within agent-based models, putting this into practice. Thanks very much, and see you folks